We are very happy to have Jiahui, who is a, fourth year PhD student of SAS in the University of Hong Kong. And she is supervised by Stephen and Philip, also working very closely and supervised by Professor Ling Peng from Department of Computer Science in HKU NLP. And her research interest lies in NLP, including pre-trained language modeling, automatic machine learning, and multimodal learning, especially on visual language. And in today's talk, she will discuss the use of large-scale pre-trained language models in zero-shot learning, and introduce a data generation-based paradigm. Okay, so Jiahui.
Okay, it's really my honor to have the opportunity to share our recent work here. Currently, can everyone see my screen? Hello? Okay,
Yeah.
okay, thanks very much. So here I would like to introduce two of our works. The first one is the efficient zero-shot learning via data generation. So this serial work was first conducted in last year, and at that time we found that the prompt-based zero-shot learning is much less accurate, and the pre-trained language model's potential for zero-shot learning has been underexploited. However, if we want to conduct instruction tuning for zero-shot serialization, it will rely on a large number of cross-task annotated datasets and to train a gigantic model size, which is unrealistic for the research community. So based on this situation, we are thinking about can we further explore the pre-trained language model zero-shot learning ability. So based on this situation, we propose our first paradigm, the zero-gen, efficient zero-shot learning via data generation. In this paradigm, the main idea is that in terms of our target task, we will first design the task-specific instruction prompt, and we will use that to prompt a large language model. Then we will utilize the knowledge of the large language model to generate a corpus of pseudo dataset, which is related to our target task. And we will utilize this synthetic dataset to train a tiny task model. Here we use LSTM or DistillBERT. And then we only need to train and do inference based on this tiny task model. In this paradigm, there are some appealing features. The first is that this paradigm is totally annotation-free, so no human annotation is required during the generation. And the second is that this paradigm is efficient, and it will achieve comparable efficient with its large language model counterparts with only 0.4% parameters. The third is that our paradigm is a new paradigm for knowledge distillation. This is model agnostic because it has no limitation on the student architecture. The last is that our paradigm is also can be applied to the closed resource large language model because we eliminate the need to access the parameters of pre-trained language model. And here we show some experiment results to verify the effectiveness of our pipeline. And we use the GPT-2 as the large language model and use the DistillBERT and the LSTM as the tiny task model. From the results, we can find that we mark those results that can surpass prompting method in gray, and we can find in most of those tasks, we can consistently outperform the prompting method. And the experiment task we investigate here is the text classification and the question answering and the natural language understanding. And another thing I want to mention that is the prompting is very sensitive to the prompt itself. However, in our pipeline, our generation-based method is robust to the is more robust to the instruction used to generate used to prompt the large language model for generation. So there are some advantage of our method. And we continue to find that if we increase the data scale, the final performance will improve continuously as the amount of data grows. And by increasing the data set, our framework may even outperform the supervised baseline on SST2 those tasks. But however, in our paradigm, even though there are some appealing features, there are still some drawbacks and need to be further resolved. The most important is that we should mention that the data quality and the amount is the crucial factors for the tiny task model's performance. However, the quality of generated data is not always guaranteed. So in our second work, we want to select the high quality data from the generated data for efficient zero-shot learning. So for the second paper's motivation, as mentioned before, the data generation-based zero-shot learning has achieved impressive success. The amount and the quality are the crucial factors for tiny task models' performance. And despite we can generate unlimited training data in theory, the data quality is not always guaranteed, and after few training epochs of the generated data, even though the training accuracy of the zero-gen dataset is still increasing, the actual testing accuracy of the model starts declining rapidly. This is a very clear indication of the model overfitting to the low-quality data. We also named them as noisy data. So we truly observed two major cases of noisy samples in the synthetic data set, the corrupted labels and the task irrelevant samples. Corrupted labels means that the generated data is wrongly labeled by the pre-trained language model. And the task irrelevant samples means the generated sample have no correlation or not so related to our target task. So those kind of noise data should be removed, otherwise it may damage our tiny task model's performance. In the previous work, there are also some other research work want to alleviate the data quality issue, and they adopt some the human active labeling to correct the corrected labels or revise the example. However, such method introduce considerable cost and may be unrealistic. To reduce the human intervention, there are also classical approach in the noise label literature to eliminate the effect of noise data by reweighting the samples. They heuristically design the weights according to some metrics such as the output confidence and the loss value. However, this still requires task-specific knowledge and excessive manual tuning. And there are also some other adaptive methods that can learn the sample weights in an end-to-end manner, demonstrate better performance in practice. However, even though they have achieved some remarkable success, they will rely on clean validation sets to provide guidance, which become a major limitation because in our zero-shot setting, we do not have such kind of human annotated clean data set. So to tackle these problems, we propose our framework. We first reformulate the high quality data generation problem as a bi-level optimization framework. In the inner loop, the goal of our method is to learn a set of sample weights to measure the data quality for each data point. And we want high quality samples will be assigned with high sample weights and low quality samples will be assigned with small values ranging from 0 to 1. So with this target, we first regard the sample weights as a hyperparameter, as a set of hyperparameters to weight the data points. and to train a tiny task model, which is corresponding to this equation. Here we use this set of sample weights to weighted sum the cross entropy loss to optimize the tiny task model. Ideally, if our sample weights learn well, then the optimized tiny task model should also perform well in a clean data set. So in our formulation, we would first use the sample weights to weighted sum tiny task model to optimize it, and then evaluate the tiny task model's performance on the outer loop using a clean data set. But however, in our situation, we have no access to such a clean data set. Therefore, we want to design another auto objective. We name it as noisy robust auto objective. And using this auto objective, we theoretically and empirically prove that if we use a noisy robust loss in the outer loop, then it can return the same return a set of well-learned sample weights that correctly measure the data quality, even though we're using a noisy data set in the outer loop to provide guidance. So after we and for more details about the noise robust loss, I will illustrate it later. And so for this framework, let me illustrate it more clearly. The first inner loop is corresponding to the second equation. Here, we use the sample weight to weighted sum the cross entropy loss, train the tiny task model. And here we build the connection between the sample weights and the model parameters. And in the outer loop, we use a noisy robust loss to evaluate the performance of the tiny task model, and which is corresponding to the first equation. Here, we build the connection between the model parameters and the outer noisy robust loss. So combine these two iterations together, we can build the connection between the sample weights to the outer loss. So therefore, we can calculate the gradient and update the sample weights iteratively with the guidance from the noise robust loss in the outer loop. And we will perform the iteration until we achieve a minimal noisy robust loss in the outer loop. Yeah, so after we finish that, we can prove that we will learn a set of sample weights that can correctly measure our data quality. For more details about the noisy robust loss, I would like to give some illustration. The noise robust loss is first investigated in the noise level learning literature, and there are some previous work has shown that there is a family of loss function that can have consistent global minimum on the neighbor noise setting. So more formally, it says that when the majority of the training data are correctly labeled, the global minimizer of the noise robust loss is the same, no matter the training data is clean or noisy data. So, and they theoretically prove that the reverse cross entropy loss is a kind of the noise robust loss. So we also use this loss as our outer loss in our framework. So with such good theoretical property, you may ask why we do not directly use such a noisy robust loss to optimize our tiny task model. The answer is that even though with a good theoretical property, it cannot empirically to optimize the sample parameters, to optimize the model parameters. To illustrate that, we made some further analysis. We first plot the loss surface of the reverse cross entropy loss and cross entropy loss. The reverse cross entropy loss is corresponding to left-hand side, and we can find that if the solution is not close to the optimal position, then its gradient is flat and hard to be optimized. So this kind of noise robust function is hard to be empirically optimized. And for the right-hand side, for the commonly used cross entropy loss, it will be more easier to be used to optimize the model parameters. However, the coarse entropy loss will emphasize more on the hard samples, which will in our noisy data setting, it will overfit to those noisy data. So it is also unrealistic to use such kind of data to fine-tune our tiny task model. And part of this, we also made some other empirical analysis using one loss function to optimize the model and use another function to measure the model trajectory. Here, the left-hand side, we use the coarse entropy loss to optimize the model and use the right-hand side to measure the model trajectory. We have found that the model's loss can significantly decrease, and meanwhile, the RCE loss will show the similar trends, which prove that the reverse coarse entropy loss can accurately measure the model performance. However, if we use the reverse coarse entropy loss to optimize the model and use the coarse entropy loss to evaluate the model trajectory, we will find that the model loss will no longer will hardly decrease. This also empirically shows that the reverse coarse entropy loss cannot empirically optimize the model parameters. This is also the reason why I do not use it to optimize the tiny task model using the noisy dataset. Instead, we will use the reverse coarse entropy loss as the guidance in the outer loop to update our sample weights, because by doing this, we can narrow the sample space from the huge model parameter space to the sample weight space, which is much smaller and easier to be optimized. This is our motivation for using the noise robust loss. And we also provide some theoretical analysis, which shows that with some minor assumptions, we can theoretically prove that our bilevel framework can uniquely return the optimized sample weights and the model parameters with only noisy data, which is the same as using a clean dataset in the outer loop to provide guidance. This theoretical proof is first conducted in the infinite sample space. We also generalize it to the finite sample space, and we find that our optimized model parameter in the finite sample space will close to the optimized model in the infinite sample space, which will be bounded by a small value. And here we would provide more experimental results to illustrate the effectiveness of our method. So here we use the synthetic dataset to train the tiny task model. The data scale is 200,000, and we we compare several baselines. The first is the supervised baseline, which use the human annotated data to train the tiny task model. The second is the prompting method, and the third is the zero gem baseline, which is directly generate the data set without any selection. And we can find that our zero gem method, if the model trained on our selected data, then the model performance can significantly surpass the zero gem and prompting method. It sometimes may even achieve comparable performance with supervised setting. And another thing I would like to mention is we can find that for the LSTM model, the improvement gap would be much more significant. This is because the LSTM model is trained from scratch, and for the distilled which is a pre-trained model, and there are some previous paper shows that the pre-trained model will be more robust to the noisy samples. So here is some illustration. And we also made some, we also plot the loss surface of the tiny task model trained on our selected data. And we can find that currently the training accuracy, as our selected data are high quality data, the training accuracy will going to a very high value, rapidly. And however, for our testing accuracy, we will no longer decreasing. Instead, it will gradually increases. Here, the results proves that our method can successfully remove those noise data from our data set, and our tiny task model will no longer overfit to those noisy data. Apart from those theoretical proof, we also provide some empirical proof to investigate whether we use a noisy dataset to provide guidance is the same as using clean dataset in the outer loop to provide guidance. We made some experiments on these 4 tasks, and we find that in our framework, even though we use a synthetic dataset, the optimized the selected data can still performs well and achieve comparable or even better performance than using a clean dataset to provide guidance. We also compare our method with some popular denoising pipeline in the noise label learning literature. And we compare the confidence coefficient and metaweight net, those popular baselines. We can find that our method can significantly surpass those baselines. There are also some training strategy can make the model more robust to the noisy samples, such as label smoothing and temporal ensembling. We also compare our method with those training strategies, and we can find that we can still surpass those training strategies. And another thing I would like to mention is that we directly select a subset of high quality data and train a tiny task model on this subset. However, for those training strategies, they will still need to train the model on the entire data set. So the SungGen method will be more efficient. Based on our learned sample weights, we can also generate diverse subsets of different data sizes. And the result in the table shows that a small data set with high quality samples can achieve better performance than using the entire data set to train the tiny task model. And which shows that the low quality data will damage the model performance significantly. And we also find that in the IMDb dataset, with only around 2% data, we can achieve better performance than using the entire dataset. So it is a very interesting result. We also plot the histogram of the learned sample weights on the synthetic dataset. We can find that the histogram will gradually be separated. And this proves that our method can successfully differentiate those high-quality data from those low-quality data. And we also made some analysis on the data diversity and the correctness. And we measure the data diversity using the self-blue score. And we can find that the generated data is more, and the smaller value would show the data set is more diverse. And we can find that the generated data would be more diverse than the human annotated data. Besides, our selected data would be would be more diverse than the zero-gem baseline. We also measure the correctness using the Roberta large as the Oracle model. We can find that the zero-gem method, the correctness of the generated data is not so would not be higher than the gold data, but however, it's also acceptable. And also, we can find that there is an interesting phenomenon. We can find that for the Amazon and the Yelp, our selected data, the correctness of our selected data even slightly lower than the zero-gem baseline. To further investigate this phenomena, we also calculate the bottom samples and the top samples correctness. The bottom samples means those data with lowest sample weights, and the top samples means the data with the highest sample weights. We can find that those bottom samples are truly those low quality data, but for the top samples, their correctness is still slightly lower than the average of our SunGen method. Actually, this is expected because we evaluate our correctness use the Roberta large as our oracle model, and it is expected that those samples with high correctness may be those redundant or too simple. But those challenging and informative samples is hard to classify and have low correctness. This illustrates that our method can select those informative and challenging samples. Here is a table doing the data visualization, which also proves our previous conclusion. Because we can find that the data with large weights are those transitional complex sentences, which is hard to be classified. And we also find that in the automatically learned sample weights, those data with small weights are those noisy data with noise label or unrelated to our target task. Those samples are selectively removed. And here are some prompts, and I will not illustrate more. And apart from this serial of zero-shot learning, efficient zero-shot learning, they work in the last year. We also conduct some new research work recently, and I would like to also share them here. So this paper I want to share is the data GPT. So detect what you need via reasoning. This is also a pipeline that tuned by the data by the pre-trained language model generated data. So the motivation for our this paper is that despite the success has achieved by previous open vocabulary detection system, this still requires humans to provide specific object name, which is neither user-friendly or realistic because there are some restrictions. Firstly, human users need to provide Firstly, human users sometimes tends to provide high-level instructions, which may not explicitly contain the objects of the interest. The second is that the constraint of the human knowledge often hinder the users to provide object names. For example, the user may wish to identify the fruits with high vitamin K, but they may lack the knowledge to determine which fruit can fulfill this requirement. So as this situation, the original object detection solutions are not applicable. And in this paper, we propose a new task named reasoning-based object detection. In this task, users will provide some abstract queries using natural language, and the model will analyze both the image and the user input, reason about which object in the image may fulfill the user's goal, and finally detect their location in the image. Here is an example. The user said that I want to have a cold beverage. Then the language model will analyze the image and think about where there is no visible beverage, where can find it. And based on the knowledge stored in the large language model, they may find that, okay, there is a refrigerator it might have. So it will detect this refrigerator. Actually, understanding the abstract instructions and have the ability to locate effectively are very crucial for domestic robots. And here is some demonstration to further illustrate this task. During the demonstration, users can request the model to find food that can help lower the high blood pressure by providing an image. The model will then suggest options such as bananas, carrot, and apples, and subsequently detect those fruits for the user. This approach can eliminate the need for user to explicitly name the objects themselves, and the model can retrieve the relevant common knowledge directly. This makes the process more feasible. And our framework is very simple. Um, we construct a two-stage detection framework for initial investigation. And in this framework, our first step involves utilizing multimodal inputs to interpret the user instruction and reason over the visual scene to identify objects that match the user's instruction. Subsequently, we will employ a frozen detector for accurate localization of the identified objects. Our training stage is following mini-GPT-4. It has two stages. In the first stage, we conduct text-image pre-training, and in the second stage, we conduct instruction tuning using our generated question answering instruction data. After the first stage, although the model is able to generate detailed description based on the image, it's not able to well interpret the human interaction and derive objects that fulfill the user's goal. They tend to output redundant objects that are not shown in the image. Hello? Okay, and they may sometimes.
Nothing wrong. We can hear you.
Okay. 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 For the after the first stage, this model may even give the object that's unrelated to the user's instruction. Therefore, we continue our instruction tuning, which is proved as crucial step that empower the vision language model to comprehend the fine-grained image feature and derive the objects of interest given the user's instruction. So to generate the multimodal instruction data, we use the ChatGPT to generate various type of instructions. One main type is to utilize the essential objects to achieve a specific goal. And for the detailed prompt, can refer to our original paper. And another thing I want to mention is the generalization ability. Even though we only fine-tuned the instruction on 80 common objects in daily life from the COCO dataset, the trained model can even demonstrate remarkable generalization ability. For example, it can even detect the cracks in the wall when prompted with a user query to identify potential dangers to humans. So this observation suggests that our model has a strong understanding of the complete visual feature during the initial training stage, and it can effectively learn the pattern to detect the object of interest during the second stage of instruction tuning. Yes, I think this is the three works I want to share here. I don't know whether anyone have any problems.
好的，那感谢佳慧。那个 Q&A 环节，黄迪你把录制关掉了，我们用中文就好了。
哦，好的，好的。
行。